Hello, here's a quick pair of thermodynamics exam questions for a bit of practice. So we start off here, state Boyle's law. So we want to say that the pressure is inversely proportional to the volume for a fixed mass of gas at constant temperature. So it's important that you put those last bits in, fixed mass of gas at constant temperature, otherwise the whole thing just falls apart and it's not actually true. So turn all of that into a sentence, or you can say that P times V is a constant. I mean, that's the other way you can do it. For a gas which obeys Boyle's law, sketch a graph of P against V and P against 1 over V. Right, so P against V, because they're inversely proportional, is going to be looking like that. That's one of my better curves. And then P against 1 over V, well, they're proportional. So we're now going to get a straight line going through the origin. So that's fine. A cylinder of fixed volume of that is filled with nitrogen gas at a pressure of 5 times 10 to the 5 pascals, temperature 15 degrees C. There's the molar mass of hydrogen. Calculate the number of moles of nitrogen in the cylinder. So we're going for our PV equals nRT. That's the one that we want because the little n is the number of moles. So little n is going to be pressure, which is 5 times 10 to the 5, multiplied by volume, which is 0.04, divided by R, which is 8.31, and by T, which, what did they say, 15 degrees, so that's 288. And that is giving an answer of 8.3567, so we'll say that's 8.4 moles to two significant figures. After a period of 100 days, the pressure has fallen to 4.5 from 5.5 from 5 times 10 to the 5 pascals at the same temperature because of leakage. Calculate the mass of nitrogen that has escaped. Right, well, that's a tenth of it has gone because we've lost, well, we've gone from 5 down to 4.5. So that's a tenth has been lost. So we're going to have so 1/10 is lost. So that means we've lost 0.83567 moles. And they've given us the molar mass. So we just need to multiply that by 0.028, and that's going to give us the mass, which is 0.0233988, so 0.023 kilograms to two significant figures. Right, that was a nice straightforward starter question. Right, the table shows the specific heat capacities C of alcohol and water. An alcohol thermometer is placed in 80 grams of water at 20 degrees C. The mass of alcohol in the thermometer is 0.05 grams. Water is then heated from 20 degrees to 60 degrees. Calculate the ratio of the energy required to warm the water and the energy required to warm the alcohol. Okay, well, we know that the energy in all of this is E is mc delta T. So we're just taking a ratio of these things, and the temperature change is the same. So this ratio here, that ratio is going to be equal to the mass of the water. Oh, I've given them both in grams, so let's stick in both in grams. So we've got 80 grams of water multiplied by the specific heat capacity of water. We can ignore the delta T because that just cancels what we have on the bottom. We can then divide that by 0.05 times 2460, and that's going to be all that we want, really. So what we're going to get out of that, we are getting 2718.7. So we'll say 2700 to two significant figures. State and explain a useful situation in which the very high value of specific heat capacity for water is useful. Right, well, we could say, I mean, anything where you wanted to take energy away, really. So you could say sweating. You could have, well, putting out fires. I mean, you only want one of these things. because they've only asked for one thing. And the reason is that you can take away a lot of energy for a relatively small change in temperature. A lot of energy for a small change in temperature. Right, that's all good. So that's that one. Now we've got an experiment run. Right, we've not much space to put it in. Describe an electrical experiment to determine specific heat capacity C of a liquid. Right, so they specifically said it's an electrical experiment, so we can't do anything like method of mixtures or something like that. We need to do the one where you've got the heater, the electric heater inside the beaker. So we can have our beaker. Let's just have a quick look ahead to see if they're doing a way of improving. Yeah, see the last bit here, possible sources of uncertainty, how these could be reduced. You've got an option of putting in insulation later on. So I'm just going to do a beaker with you're going to want a thermometer in it. So draw your thermometer, have your liquid coming across. We're going to then have the heater going in. So we have our electric heater. That can come out, go to our power supply. We're going to want an ammeter so we can measure the current. So that has to go in series. And we're going to want a voltmeter in parallel so we can measure our voltage. So you're going to want to label all of this. Obviously, you've got the liquid, you've got the thermometer, you've got the heater, you've got the voltmeter, ammeter. You don't really need to label, but you could do if you wanted. Right, so that's our diagram, label diagram. I haven't put the labels on, but you know, it's easy enough. List the measurements to be taken. Right, in this you want the equations that we're going to use to be your guide on this, because we're going off of our E equals mc delta T. So we've got that. So we know that C is going to be E over m delta T. And we know that the energy supplied is going to be our power times time. So that is our volts times amps times time divided by m delta T. Now they've asked that for the third bit, an explanation of how you determine that. But doesn't that just make things so much easier for then saying the list of the measurements that you're going to take? Because you need to, well, it's all of these things on the right hand side. You need to measure the voltage, the current, the time that the power is being supplied for, time of power supply. You need to do the mass of the liquid and the temperature change, which I'll just put here, delta T, so the temperature change. So that's 5 things that you need to measure. Possible sources of uncertainty in your measurements and how these could be reduced. Right, you've got loads of things you could do here. So you could stir the liquid. That's going to get a more consistent temperature reading. That's going to get a better temperature reading. You could insulate the beaker. So that's another one that we could have. So even better if you know the specific heat capacity of the insulation. But if you insulate the beaker, then you're going to get a better calculation for E, better E calculation, or a more accurate, is probably a better way of putting it. So more accurate E calculation. So because we've got lower losses to the surroundings, so more of the energy from the heater is going to stay in the liquid. Yeah, you can include specific heat capacities. You can have the one as well that don't just take the temperature reading as soon as you've turned off the power supply, because it can take, there's a little bit of lag, isn't there, of getting that extra sort of last bit of energy out into the liquid and then it being recorded by the thermometer. It's not an instant thing, so you could always have that as well. But you can see you're getting loads of marks here. I mean, you've drawn a label picture, you've got 5 different things you're going to measure, you've got 2 equations that you've combined and rearranged, and then you've said a few ways of improving things. So it's just mark central there. I mean, there's loads of ways you can pick up everything required. So yeah, that was 2 fairly short questions, but nice ones to keep the practice moving along.